Navokoj, a general-purpose engine for finding coherent structure inside astronomically large discrete spaces.
This video introduces Navokoj, a constraint intelligence platform, which is also a general-purpose engine for finding coherent structure inside astronomically large discrete spaces. Let's begin by discussing what constraint intelligence is. Classical solvers use guess and check with backtracking. This approach leads to exponential complexity and timeouts. At Navokoj, we take a statistical mechanics approach to logic, turn them into a dissipative dynamical system, where the correct assignment has the lowest energy state and can be reached via a numerical simulation of an adiabatic quasi-static process. The core problem is the increasing complexity of decision-making due to various constraints. At Navokoj, we still face the problem, but we have shifted the boundary by quite a margin. With our tech, companies can obtain best feasible solutions at extremely large scale within an hour, and medium-scale problems are optimized for satisfaction within 10 seconds. Navokoj offers a new approach. It integrates constraint handling into intelligent decision-making processes. Our core math is arithmetic symmetry breaking, which is transferable to the domains like AI, and which we have used to go to deep global basins, which current state-of-the-art survey propagation fails to. The goal is to move beyond simple optimization toward a comprehensive understanding of constraints and their impact. Navokoj Pro Engine is our first step towards that. Navokoj has shown its mettle at scale, solving increasingly harder and harder problems within a time window of 1 hour. While we do not claim to have cracked the nut of NP-hard problems, real-world scale problems like chip verification, air traffic control can be handled by Navokoj. We have tested this thoroughly, and it shows stability and consistent 95% plus clause satisfaction in the SAT regimes. Our beta API is open till June 2026. Standard compute is on CPU. For faster convergence, we offer L4 and H100 GPU executions for large-scale problems. Navokoj's total addressable market is huge. In the domains where close to perfect constraint satisfaction is preferred within 1 minute, Navokoj dominates. We have tested this with chip verification, portfolio optimization, logistics scheduling, workforce scheduling, and Kubernetes pod orchestration, and more. Future roadmap includes integrating a neural compass engine, which helps converging to global basin faster and faster, enabling us to solve truly astronomical scale constraint satisfaction problems.
Welcome to this video on operator algebraic approaches to constraint satisfaction, an introduction to the mathematical foundations of spectral arithmetic dynamics. We present a new perspective on SAT solving by reframing it using operator algebras and thermodynamics. We treat SAT as a, quote, fake quantum system to leverage the math of phase transitions and the Riemann zeta function for gradient descent, enabling multi-basin exploration near criticality. Algebras are operators on infinite dimensional spaces, closed under addition, multiplication, norm, and involution. They model quantum observables and states, providing a framework to encode SAT instances. Dynamical systems involve a C algebra and time evolution via a one-parameter automorphism group. Hamiltonian-driven time evolution is defined by alpha of A equal to e to the power of iota ht, multiplied by a e to the power minus iota ht. The Gibbs states, or equilibrium states, are determined by the inverse temperature beta and the partition function z. The Boscoin system embeds number theory into a C dynamical system. Its partition function becomes the Riemann zeta function. A phase transition occurs at beta equals 1, linking prime distribution with quantum statistical mechanics. Graph Laplacians, like the combinatorial Laplacian L equals dA, are positive semi-definite, and their eigenvalues encode spectral information. In SAT, the Laplacian captures instance rigidity, with vertices as clauses and edges as constraints. The Shunya bar construction combines arithmetic and geometric sectors for SAT solving. The geometric sector provides constraint rigidity information. The arithmetic sector uses the heat trace, which encodes thermodynamic properties weighted by inverse temperature beta. We introduce a controlled perturbation that couples the Bose-Cons arithmetic sector to SAT violations. The arithmetic susceptibility diverges near s equals 1. In the gradient flow, this divergence acts as a dynamic gain amplifier, increasing the descent force near the arithmetic critical point. Symmetry breaking creates a multi-basin landscape for SAT solving. In the arithmetic sector, the unique KMS state for $beta leq $1 splits into infinitely many states for $beta greater than $1, characterized by arithmetic characters. This modulates clause weights, creates RSB-like phenomenology, and provides observable diagnostics. We gain 4 key advantages: global guidance from spectral information, arithmetic amplification near criticality via the zeta pole, multi-basin exploration through character modulation, and smooth interpolation between random and optimal states, avoiding combinatorial traps. Key mathematical objects include C algebras and C dynamical systems, KMS states, the partition function, the Boscan system, the Riemann zeta function, and arithmetic susceptibility, all central to this approach. In the FAQ, we address why we truncate the Boscan system, managing susceptibility divergence with large coupling, replacing the sigmoid with smooth approximations, and the advantage over simulated annealing due to arithmetically driven gain. For further reading, explore the mathematical foundations of Bose-Cone, statistical mechanics of computation, and spectral graph theory. Thank you for watching this video. See you with a more practical and hands-on video next time.
Welcome to this hands-on Constraint Intelligence Lab, where we'll explore how Navokoj works under the hood. First, consider a 5 SAT star plus chord pattern. The initial state is symmetric. Gradient calculation shows the hub variable receives massive pressure, leading to a symmetry break. Next, let's examine a 5-variable mixed logic SAT problem. The initial state is symmetric. The gradient calculation reveals that forces from complex clauses cancel out. The net force from a simple clause pushes one variable up, breaking the symmetry. The 4-variable shifting square challenge demonstrates critical behavior. Initial symmetry causes forces to cancel out for some variables. Adagrad then breaks the symmetry, causing one variable to rocket up and leading to a cascading effect. The 5-variable Shunya bar SAT run illustrates the critical sweep. Snapshot 1 shows a stalled start. Snapshot 2 features a critical fluctuation with an arithmetic kick. Snapshot 3 shows a frozen solution with a persistent arithmetic hum, stabilizing the result. This 5-clause SAT problem has a 2-dependency chain and a conflict. The initial state is symmetric. Gradient calculation shows one variable feels strong pressure to go down, initiating propagation. The symmetry breaks, and the chain reacts. Adagrad addresses unsat pressure. At the symmetric start, only one variable has a gradient. The Adagrad update then breaks the symmetry, pushing one variable up. Adagrad remembers this push and controls the subsequent steps, which is ideal for unsat pressure. Navokoj uses the heat kernel and SAT Laplacian for decoherence on the graph. The Laplacian matrix L measures local connectivity. The heat kernel spreads influence across the conflict graph, rapidly driving separation and breaking symmetry. The Shunya bar system mathematically reconstructs the solver, factoring the partition function into arithmetic and geometric sectors. This leads to the critical sweep from a high T state to a frozen ground state, which enables solution discovery. To speed up decoherence, Navokoj uses zeta pole tuning at the singularity. By scaling the dynamic kick by the zeta magnitude near the pole, the kick magnitude explodes, forcing variables to instantly diverge in unique directions. Navokoj is a general-purpose engine for finding coherent structure in large discrete spaces. It aims for best effort success, returning the closest possible solution with precise diagnostics when a perfect solution is impossible. This chart illustrates the SAT phase transition sweep. The nano solver shows smooth degradation. The pro solver exhibits a sharp increase in solve time near the critical phase transition, but maintains high satisfaction. The clause density versus performance data shows how solve time scales with problem complexity. For high-density problems, Navokoj's computational leverage solves SAT instances that are typically inaccessible to classical heuristics. DEFEKT is the diagnostic intelligence component, providing an MRI-style scan for logical problems. It predicts solvability, enables cost control, helps with constraint debugging, and automatically selects the right hardware and engine for smart routing. These are the engine benchmarks across industrial SAT instances. The PRO engine is used for mission-critical verification, Mini for balanced optimization, and Nano for ultra-fast real-time feedback. The Navokoj API is open until June 2026. You can check out the platform at navokoj.shunyabar.fu.